This video describes crosslingual generalization through multitask fine-tuning. The study was released on arXiv in November 2022 by Muennighoff et al. In a paper of the same name. The work, which was conducted as part of the BigScience Workshop, also introduces the BLOOMZ and mT0 models. Let's start with the motivation. It has become clear that large language models with sufficient pre-training are able to solve some tasks without being explicitly trained for them, as notably shown by GPT-3. It has also become clear that fine-tuning large language models on groups of tasks boosts their zero-shot task generalization, as highlighted by works like FLAN, T0, and MetaICL. To date, the work exploring this latter direction has primarily focused on English models and tasks, but a growing body of work has shown that multilingual large language models also show zero-shot abilities, with examples such as XLM RXXL, XGLM, MT5 with SAP, and Alexa Teacher Model. However, their zero-shot performance still trails significantly behind the performance attainable with task-specific or language-specific fine-tuning. This gap is hard to address for low-resource languages and tasks with limited data, where collecting a fine-tuning corpus is difficult. The goal of this work is to tackle this issue by studying the potential of multilingual multitask fine-tuning to improve zero-shot generalization on non-English tasks. Some of the key findings of this work include, first, English multitask fine-tuning improves performance on non-English held-out tasks. Second, fine-tuning on multilingual data further helps performance. Third, larger multilingual models benefit more from multitask fine-tuning. And fourth, fine-tuning enables a degree of zero-shot task generalization on languages that were not intentionally seen, or very rarely seen, in pre-training. In order to study multilingual fine-tuning, a new collection of prompts called XP3 is constructed, which adds 28 multilingual datasets to the public pool of prompts, also known as P3, used in the T0 work. XP3 includes 4 new task clusters: translation, simplification, program synthesis, and a loose category known as code miscellaneous, which includes tasks like estimating the computational complexity of a code snippet. In more detail, the XP3 datasets include multiple choice QA, extractive QA, closebook QA, paraphrase identification, sentiment, topic classification, summarization, word sense disambiguation, structure to text, simplification, program synthesis, code miscellaneous, translation, co-reference resolution, sentence completion, and natural language inference. Here, datasets in XP3 that are added beyond those in P3 are highlighted in bold. Datasets used for training are in yellow, while those used for evaluation are in green. One aim with XP3 was to replicate the language distribution of the roots dataset used to pre-train BLOOM. As such, the same 46 natural languages in code are used. We can visualize this distribution by plotting language on the x-axis and percentage of the corpus corresponding to that language on the y-axis. Here's the plot. The colors correspond to maroon for XP3, dark blue for roots, and orange for the corpus used to train MT5. Broadly, we see that XP3 and roots have similar distributions. At the head, XP3 is 39% English, while roots is 30% English. At the tail, we have African languages like Tree, sourced from the Flores 200 dataset. To study non-English prompts, a variant of XP3 called XP3 MT is constructed by machine translating the prompts from monolingual datasets from English into the language of the underlying dataset, using the Google Cloud API for translation. Since there are several dataset variants used in this work, it's helpful to see how they relate to each other. The first is P3. It contains English datasets. Here is a sample from the pause dataset, where we asked to determine if sentence 2 paraphrases sentence 1. The prompt used with each such example is also in English. For this sample, it takes the following templated form, providing the 2 sentences and asking the question, can we rewrite sentence 1 to sentence 2, yes or no, before offering choices. The second dataset variant is XP3. This contains multilingual datasets. Here, for example, we are showing the corresponding human-translated Spanish variant of the sample we just saw in P3 that forms part of the pause-X dataset. As with P3, the XP3 prompts are English. For this sample, the prompt matches the one used in P3. Finally, the third dataset variant is XP3 MT. This also makes use of multilingual datasets. Here we show the same sample from exports. This time, however, the prompts are machine translated from English into the language of the underlying dataset. So for this example, the prompt is translated into Spanish. In the experiments, two families of models are fine-tuned. The first is the family of BLOOMZ models. These are decoder-only models similar to the architecture of GPT-3, ranging in size from 560 million parameters up to 176 billion parameters. These models have been pre-trained on the roots corpus for 350 billion tokens. They are fine-tuned for a further 13 billion tokens. During fine-tuning, the loss is only enforced at the target tokens. So for example, given an input like translate to English je t'aime, together with the space-separated target I love you, the loss is only enforced on the latter sequence. The second family of models is MT5, which consists of encoder-decoder architectures ranging in size from 300 million parameters up to 13 billion parameters. These models have been pre-trained on MC4 for 1 trillion tokens. The models are fine-tuned following a similar regime to BLOOMZ. However, there is a slight difference in fine-tuning, in that inputs are fed into the encoder rather than space-separated from the target as they are with BLOOMZ, to account for the difference in architecture. By combining the different datasets and model families, 6 fine-tuned variants are produced. These are models fine-tuned on P3, referred to as BLOOMZ P3 and MT0 P3. There are models fine-tuned on XP3, referred to as BLOOMZ and MT0. And there are models fine-tuned on XP3 MT, referred to as BLOOMZ MT and MT0 MT. Fine-tuned models are evaluated on 3 held-out task clusters: co-reference resolution, sentence completion, and natural language inference. They are also evaluated at program synthesis on human eval to provide some measurement of their coding abilities on this popular benchmark. Note, however, that this is not a held-out task cluster. To evaluate on tasks that involve completion, rank classification is used to select among options by scoring them under their log likelihood, as done in prior work like GPT-3 and T0. During evaluation, on each dataset, 5 prompts are randomly chosen from prompt source and used for all language splits. The median score of the 5 prompts per language split is reported. Finally, generation evaluations are assessed using the LM evaluation harness implementation. We now turn to results for zero-shot multilingual task generalization for sentence completion on Xcopa and XStoryClose, starting with the baseline models of XGLM 7.5b scoring 51.8, BLOOMZ scoring 52.9, and MTK Instruct 13b scoring 50.4. With P3 fine-tuning, BLOOMZ P3 scores 80.5. With XP3 fine-tuning, BLOOMZ scores 82.6, while MT0 13b scores 86.0. Broadly similar trends are observed for natural language inference. For co-reference resolution, the first 2 baselines perform similarly. This time, MTK Instruct 13b slightly outperforms BLOOMZ B3, while BLOOMZ and MT0 13b remain the strongest models. Some observations here are that first, MT0 outperforms BLOOMZ, despite the fact that the latter has many more parameters. Some possible explanations include that MT0 uses longer pre-training, it sees 1 trillion tokens rather than the 366 billion tokens seen by BLOOMZ, and that it uses an encoder-decoder architecture with a masked language modeling objective, which seems to perform well with fine-tuning, as highlighted in recent work by Wang et al. And Te et al. A second observation is that MT0 outperforms MTK Instruct 13b. This may be in part due to a difference in the prompting style used during fine-tuning, with the MTK Instruct prompts being more structured. Third, we observed that XP3 fine-tuning outperforms P3 fine-tuning. Further analysis, not shown in this chart, finds that this trend also holds when considering only the English tasks. A plausible explanation here is that simply adding additional tasks and prompts helps generalizations, as highlighted in recent work by Chung et al. We now turn to the question of language generalization. A first comment can be made here by looking again at the plot we just saw and focusing in particular on BLOOMZ and BLOOMZ P3. We can make the observation that BLOOMZ P3 strongly outperforms BLOOMZ. This is intriguing since it suggests that zero-shot multilingual task performance improves after fine-tuning on English-only prompts on languages that were only seen during pre-training. This finding has major potential benefits, since it is particularly hard to collect low-resource language data, so improving performance on these languages using English data may be more tractable. The next study examines performance on languages that were never intentionally seen in training. This slightly odd terminology is used to account for the fact that due to the scale of the pre-training corpora, it's hard to be confident that exactly no data in a given language has been seen. Performance is evaluated on natural language inference for Bulgarian, German, Greek, Russian, Thai, and Turkish. Here, the colour bars represent BLOOMZ 7.1b, BLOOM, BLOOMZ 7.1b, and BLOOMZ. We first see that XNLI performance improves with BLOOMZ across all languages. Note that chance performance here is 33%. In practice, it is found that tiny fractions of these never intentionally seen languages do appear in the pre-training corpus, albeit very rarely. An analysis estimates, for example, that Thai in fact constitutes 0.006% of the corpus. It's useful to note that further analysis suggests that XNLI labels do correlate to some degree with Levenshtein edit distances between hypotheses and premises, so it's possible that using low-level cues, such as character inspection, would suffice to outperform a random baseline on this data. Somewhat similar trends are found for co-reference resolution on Japanese and Russian. Results on sentence completion are a little more mixed, with the trend only strongly visible for Italian and Russian. The next experiments consider performance on non-English prompts by translating the XP3 prompts into languages beyond English. On XNLI, with English prompts, we find that BLOOMZ outperforms BLOOMZ mT. However, on machine-translated prompts, BLOOMZ mT works better. On human-translated prompts, we see the same trend. On XCOPA, both models score similarly on English prompts, while BLOOMZ mT does better on machine-translated prompts. We see a similar trend to XNLI on both XStoryClose and XWinograd. Broadly, BLOOMZ mT outperforms BLOOMZ on non-English prompts, but is worse on English prompts. The MT013B comparisons are more mixed. Machine translation helps on XNLI and XWinograd, but hurts on XCOPA, with mixed results on XStoryClose. For both models, human-translated prompts perform significantly better than machine-translated prompts. We can see this by comparing machine-translated prompts and human-translated prompts on XNLI, where we observe that human translations do better for both models. The next experiments study the interaction of model scale and multitask fine-tuning. We first show results on XCOPA, with model parameters ranging from 560 million up to 176 billion on the x-axis, and average accuracy on the y-axis. Here are the results. Blue represents BLOOM, maroon represents BLOOMZ, and orange represents MT0. We first see in the plot how MT0 scales particularly well with increased model size. However, perhaps the most interesting finding here is that the gap between BLOOM and BLOOMZ grows with scale, a trend that is clear in the XCOPA plots. These trends are replicated across XNLI, XStoryClose, and XWinograd. A high-level takeaway from these plots is that multitask fine-tuning benefits larger models more. We next examine how performance on generative tasks evolves with multitask fine-tuning. To provide context, we first look at how performance evolves on natural language understanding tasks, plotting training tokens on the x-axis and average accuracy on the y-axis. Here are the results, with pink depicting BLOOMZ 7.1b, maroon depicting BLOOMZ, and orange representing MT013b. Broadly, we see that natural language understanding tasks improve under multitask fine-tuning. Now, we'll look at natural language generation tasks, specifically translation and summarization, with average BLOOR score on the y-axis. Here is the plot. Although there is some initial improvement for the BLOOMZ models, we observe that natural language generation task performance worsens as fine-tuning continues longer. For further insight, we can also look at performance on human eval, in which the task is to complete functions for a given Python docstring. The metrics used for evaluation are parse at k for various k values. With this metric, higher is better. The baselines include a collection of open source models, as well as the codex variants introduced by OpenAI at the same time as the human eval benchmark. For the smallest BLOOM model with 560 million parameters, there is a boost with fine-tuning. For medium-sized models, there is a slight gain, but not much. Finally, For the 176 billion parameter BLOOM model, fine-tuning actively harms performance, producing a drop in score of approximately 3.5% for pass at 1. For completeness, we can also examine the performance of BLOOMZ fine-tuned on P3, which is significantly worse, almost certainly because the P3 fine-tuning data contains no code. Overall, we see that generative tasks do not appear to benefit from sustained multitask fine-tuning. One possible cause for the drop in generative performance is that multitask fine-tuning produces a bias towards shorter completions, which may harm performance where longer answers are required. A partial mitigation to this is to force longer generations by ignoring the end-of-sequence token when it appears in the output, which does help things a little, though it is perhaps not the most satisfactory fix. To better understand the code generation results, we can look at some qualitative examples. We'll first look at BLOOMZ generation for a snippet of code. This snippet imports a list for type hinting, provides a function header called hasCloseElements, then provides a docstring that states, check if in given list of numbers are any two numbers closer to each other than given threshold. Then it provides some examples of the desired function behavior. Given this as a prompt, the BLOOM generated output contains 10 lines of code, interspersed with some whitespace and a couple of comments. The BLOOMZ generation for the same header and docstring produces 2 lines of code. For this example, both the BLOOM and BLOOMZ generations are correct, but it appears that BLOOMZ is biased towards more concise code. To check that this is representative, we can look at the statistics for the BLOOM and BLOOMZ code generations. In terms of average characters, BLOOM generations have 247 versus 144 for BLOOMZ. In terms of average number of Python comments, there are 0.69 for BLOOM and 0.04 for BLOOMZ, which is to say that BLOOMZ produces 17 times fewer comments. These statistics support the suggestion that BLOOMZ is indeed producing more concise outputs. It is also useful to look at the statistics of the XP3 code datasets used during fine-tuning, which interestingly include a greater number of characters and comments than either model's generations. The next experiment explores how language proportions in pre-training affect the performance of multitask fine-tuned models. We first look at Xcopa, plotting the pre-training size of languages used with BLOOM in percentage points on the x-axis in log scale and average accuracy on the y-axis. Here are the results. The lines denote BLOOM in blue, BLOOM fine-tuned on P3 in purple, BLOOMZ with machine translations in red, and BLOOMZ in maroon. A broad overall trend is that fine-tuned models perform better on languages with greater representation in pre-training, though the trend has some noise and not all lines are monotonic. For reference, it's useful to recall that XP3 was constructed with the aim of matching the root's language distribution, so the fine-tuning language proportions used by the BLOOMZ models approximately match those of pre-training. Similar trends appear to some degree on XNLI and XStoryClose, while the trend is a little less clear on XWinograd. It's possible that other factors, such as differences in difficulty of the subsets of XWinograd, may also be playing a significant role here. We now turn to some qualitative results. Note that these are cherry-picked rather than randomly selected. The first considers input in the form of an English prompt. Write a fairy tale about a troll saving a princess from a dangerous dragon. The fairy tale is a masterpiece that has achieved praise worldwide, and its moral is, heroes come in all shapes and sizes. Story in Spanish. The BLOOMZ generation is:
Un reino, en el bosque, está bajo un terrible dragón. Todos los que intentaron derrotar al dragón murieron. El rey y la reina le pedían al pueblo que les diera un niño, que les gustaría salvar al reino de la maldición del dragón. Un día, la reina dio a luz a un niño, con una cabeza enorme y unos ojos que brillaban como estrellas. El rey y la reina llamaron al niño Elliot. Elliot crecería y se convertiría en un joven gigante. Él salvaría al pueblo.
The MT0 generation is:
En la noche de la primera tempestad, un gigante dragón, llamado Odín, golpeó a una princesa al dedo. Así que un troll, llamado Odín, fue a salvar a la princesa. Luego, este fue querido por todos.
To provide some insight for non-Spanish speakers like myself, these outputs have been translated to English using the Google Translate API without making edits. A kingdom in the forest was under a terrible dragon. All those who tried to defeat the dragon died. The king and queen asked the people to give them a child, that they would like to save the kingdom from the curse of the dragon. One day, the queen gave birth to a boy with a huge head and eyes that shone like stars. The king and queen named the boy Elliot. Elliot would grow up to be a young giant. He would save the town. The MT0 output translates to something like, on the night of the first storm, a giant dragon named Odin struck a princess to the finger. So a troll named Odin went to save the princess. Then this one was loved by everyone. This translation sounds a little odd, but then the Spanish generation produced by the model is also not perfect. We can also look at the effect of forcing longer generations to tackle the bias towards short generations mentioned earlier. Given the input, why is the sky blue? BLOOMZ generates a slightly nonsensical repetition of the question. BLOOMZ answers Rayleigh scattering, while MT013b answers because of the sun. Enforcing a minimum output length of 10 tokens by ignoring the end of sequence token changes the BLOOMZ output to Rayleigh scattering. The blue color of the sky is due to Rayleigh scattering of sunlight by atmospheric molecules. The MT013b output becomes because of the sun's radiation's sensitivity to light. So we see that while this technique is a little crude, it can bring benefit. For those curious, you can find the answer to this question here and in the video description. This work relates to several themes in the existing literature. First, there's work demonstrating that multitask prompted fine-tuning, also known as instruction fine-tuning, brings a boost to zero-shot task generalization, a fact highlighted by work such as T0 and FLAN. This work particularly builds on the T0 study, as well as the prompt source tool used to gather the P3 dataset for that work. As part of this broader theme, a range of work has shown that increasing the scale and diversity of tasks and datasets used during fine-tuning brings benefits. This includes Meta-ICL, BigBio, CT0, FlanPalm, and natural instructions. The majority of prior work to date has focused on English prompts and datasets. Most related to this work is the concurrent work on supernatural instructions, which trains both English and multilingual models on prompted datasets, known as TK-instruct and MTK-instruct, showing that they can achieve promising performance. To provide a point of reference, experimental comparisons are reported that compare BLOOMZ and MT0 with the MTK-instruct model produced in that work. There has also been prior work considering the question of never intentionally seen generalization. In particular, the authors of GPT-2 discovered that unintentional inclusion of non-English text enables some non-English generation. In a related manner, this work finds that multitask prompted fine-tuning enables processing of languages that were not intentionally seen during pre-training, at least to some extent. Finally, there is prior work on multilingual models, which aim to enable processing of multiple languages, particularly beyond English. These include works like XLM, XLMR, and M2M100. Two particular families of architectures have emerged as useful for this setting. There are encoder-decoder models like MBART and MT5. Then there are decoder-only models like MGPT, XGLM, and BLOOM. This work builds on MT5, which is fine-tuned to produce MT0, and BLOOM, which is fine-tuned to produce BLOOMZ. Let's now turn to the key takeaways of this work. Fine-tuning on English-only data in the form of P3 helps a multilingual model generalize to tasks in other pre-trained languages. Fine-tuning on multilingual data in the form of XP3 brings even better performance. Fine-tuned models can generalize to languages never intentionally seen in pre-training or fine-tuning, at least to some extent. Fine-tuning on machine-translated prompts can improve non-English prompt performance, though can harm English prompt performance. Larger models benefit more from fine-tuning. Lastly, fine-tuning on short targets may bias models to produce short outputs, hurting performance on generative tasks. The assets released as part of this project include XP3, a corpus of tasks in 46 languages, together with a variant comprising machine-translated prompts known as XP3MT. In addition, all trained models produced as part of this work are made available. These include BLOOMZ and MT0. Before closing, we'll briefly discuss a few low-level nuts and bolts of the fine-tuning process for those interested. When fine-tuning BLOOM, the token loss is scaled to the length of the target sequence that it belongs to, since targets vary in length. For example, multiple-choice QA targets are typically much shorter than translation targets. Samples that are longer than 2048 tokens are skipped, and packing is used to train efficiently on multiple samples concurrently. The final checkpoint used for evaluation is chosen based on validation performance. For MT5 fine-tuning, much of the process is the same, with the exception that, as mentioned earlier, inputs are processed by the encoder rather than space-separated and passed into the decoder. Fine-tuning is performed with the T5X framework on TPUs. In the video description, you can find links to code and models, slides, and references. Thank you for your attention.